and invite Chris Peaster here to introduce his student, Michael Lorek.
All right. Mike wisely gave me a printed bio to read so that I would not extemporize up here. So Michael Lorek is a Cleveland native, got his BS in electrical engineering from Ohio University in 2009. He's been working with me here ever since on his PhD in electrical engineering and computer sciences. Michael's held various positions outside of academia, including internships at Advanced Micro Devices in 07-08, Qualcomm in 11 and 12, and a research fellowship at NIST in 2009. His current research interests include on-chip magnetic field sensing, energy harvesting interface circuits, and sensor node component integration. And I'll add to that Mike has been a spectacular grad student. He's got tremendous breadth in terms of where he works. He's an excellent integrated circuit designer. He's done several chips on energy scavenging for ultra-miniature wireless sensor nodes, all the way up through writing software for the OpenWSN standards-based project and everything in between. And you'll hear him talk about two of the applications of his work right now.
Thank you, Chris, for the great introduction. Hi, everyone. I'm going to talk to you about wireless power metering at plugs and panels. First of all, I'd like to acknowledge the collaborators on these projects, Fabi and Chris, and Dr. Lanza Serra, who works at Lawrence Berkeley Lab. He's been a co-advisor on the panel submetering project. Okay, first, I'm going to talk about the panel metering. So our goal for this project is to design non-contact, stick-on electricity meter sensors, and I'm going to refer to that as SEM throughout the remaining talk. So these sensors should measure both voltage and current so that we can calculate real power. And our approach to designing these sensors is to use commercial off-the-shelf components because we believe that in large quantities, these sensors can be made for very low cost. So one advantage of using non-intrusive stick-on sensors is that they can be installed without an electrician. And it turns out for more traditional current transformer-based sub-metering installations, the electrician cost can dominate the total install cost. So with low-cost hardware and no electrician required, we believe that we can drastically reduce the total install cost and time for panel sub-metering. So next, I'd like to show you how the system works. So at the top left, you can see a block diagram of the system. So on each SEM PCB, there's a Hall effect sensor, which measures the magnetic field, a few amplifiers, and an MSP430. And the MSP430 digitizes the analog voltage and current signals and communicates with a base station over a wired bus. And on the top right, you can see a photo of the whole system installed on a panel. So here we have 5 breakers that are metered, and they are connected to a Raspberry Pi base station via a wired bus. And this whole system is powered by a single connection to a 5-volt wall transformer. And on the bottom right, you can see a close-up photo of our SEM sensor. And so it's about 19 by 12 millimeters, fits on a breaker very nicely. And it's actually very low cost. So we're excited to say that the components on this board cost about $10 in quantities of 100. So if that were to be scaled up to large-scale manufacturing quantities, we believe that it could be very cheap. Next, I'd like to show you what 2 main types of circuit breakers look like internally. On the left, you can see what I'll call a thermal actuated breaker. And you can see here where our SEM sensor would be installed. So the way this works is there's a bimetallic strip, and when the current through the breaker becomes large enough, the heat dissipated in that bimetallic strip is enough to deflect it to the point where the breaker trips. And on the right is an electromagnetic actuated breaker, and this functions fundamentally differently. So here you can see there's a solenoid in the breaker which concentrates the magnetic field by roughly 10 to 20x. And when the current through the solenoid becomes large enough, that creates a large magnetic field, and the Lorentz force that is applied to this lever here pulls it in and actuates the breaker. So you can imagine that in the design of a sensor that measures the magnetic field around the breaker to sense the current, this solenoid would be very advantageous because it essentially relaxes the requirements on the SNR at the sensor. Unfortunately, based on what we've seen, the thermal actuated breakers are much more common, and while they are harder due to the lower magnetic fields, those are the focus of this work, and all of the data I present is measured on breakers such as this. Okay, next I'm going to tell you how we actually sense the power. So again, here's a thermal actuated breaker with our sensor annotated. And so to measure the power, we need voltage and current. To measure the voltage, we effectively, there's a capacitance which is created between the high voltage energized conductor in the circuit breaker and our SEM sensor PCB. So as the line voltage changes, this induces a current through that capacitor, which is then sensed by the circuit shown here on our PCB board. And so that capacitor current is converted to voltage, amplified, and then digitized by an ADC. So I call this signal Vsense, and this Vsense signal is then proportional to the derivative of the circuit breaker's line voltage. Now, to measure the current, we monitor the magnetic field incident on our Hall effect sensor. So you can see the circuit here. There's a Hall effect sensor, some filtering, an instrumentation amplifier, and then that signal is digitized by the ADC on the MSP430. And I'm going to call that signal iSense. Okay, so now we have iSense and Vsense. How do we calculate power? So as I mentioned, the Vsense signal is proportional to the derivative of the circuit breaker line voltage. So to account for that, we built a PLL in software, which tracks the phase of this Vsense signal. And then, so it phase locks to it and then shifts by 90 degrees. And the output of the phase shift is then multiplied by the iSense signal. And the output of that multiplication is scaled by a calibration factor K, which I will describe in more detail later. So the result of that scaling is then real power in watts. Okay, so now I'd like to show you some measurements that show that this sensor works. Here you can see the real power output of our sensor compared to a reference power meter. And I make note that the y-axis is logarithmic here. And so what you can see here is that the output of our sensor correlates very well with a reference power meter down to load powers below 10 watts. And this data was taken with 16x averaging. So you can see that there's a fundamental trade-off between measurement latency and resolution in your measurement due to how much, that depends on how much you want to average. Okay, next I'd like to show some waveforms which verify the analog front-end bandwidth of our system. So on the left, you can see some waveforms which were taken using a resistive load connected through a TRIAC dimmer. So the black curve is the measured Vsense, blue is the synthesized voltage signal, and red is the measured iSense current signal. So looking at the time domain waveforms, you can see when the TRIAC dimmer is in the off state, the current is roughly 0, and when the TRIAC dimmer transitions, there is an abrupt change in the the circuit breaker's current. So you can see that here as well. So taking the FFT of this data, that plot is shown on the right. So you can see that our sensor maintains bandwidth up to the Nyquist frequency of 960 hertz. So this verifies that our sensor is capable of measuring nonlinear loads accurately. And we also installed this system in a residential building to verify its real-world performance. So what we did is we installed our sensor on a residential dwelling on the kitchen circuit. And this panel also had a TED 5000 whole panel meter installed, which served as the reference meter for our measurement. And the way we calculated the K factor for calibration, what we did is we plugged in various resistive loads to outlets in the kitchen, and we monitored the change in the output of our SEM sensor, and then we were able to correlate our sensor's output to real power in watts. And on the right here, you can see 8 hours worth of data that we logged from both our SEM sensor and the whole house power meter. And so you can see when appliances in the kitchen turn on and off, the two power meters track with each other. And since our sensor is only measuring the power on the kitchen circuit, and the reference meter is measuring the power on all the circuits on the panel, that is why these two curves are not on top of each other. Okay, so in conclusion, about the panel monitor. So this uses a standard PCB manufacturing process. We can measure real power down to below 10 watts. This slide is a bit out of date. Actually, the bandwidth the bandwidth of our analog front end is 960 hertz. We can measure current voltage, real power, and the power dissipation of the sensor itself is about 16 milliamps from 5 volts. So, the hardware is low cost. It doesn't require an electrician to install. So this represents roughly 10x lower install cost and time compared to commercially available solutions which use current transformers. So if you'd like to learn more about this, here are a few references. You could check out the IEEE Sensors Journal from last month for a long paper about this work. Okay, so now I'm going to switch gears and talk about wireless power monitoring at the plug. So on this slide here, you can see data for historical and predicted future data for HVAC and plug load power dissipation in buildings. So if current trends continue, this shows that there will be an inflection point in a few years where plug loads could start to become the dominant energy dissipators in buildings. So we have devices such as smart thermostats, which optimize and reduce the energy dissipation of HVAC. But what about plug loads? I'd argue right now there's not a good solution for ubiquitous power monitoring at plugs in buildings. So how are we going to solve that problem? Okay, so here you can see a device called Kilowatt by P3 International. I'm sure a lot of you have seen this before. And so you can get this today at Home Depot for around $28. And this, you plug a device into this, and it shows you how much power is being used on a display. And you can see the form factor is big and bulky. So this device is commonly used for, periodically auditing how much power, a few devices are using. And this is not something that is going to be installed on every outlet in a building for long-term monitoring. And the reason that this device is so bulky is due to the way it measures the current. So the way this works is it breaks the circuit and inserts a resistor in series and then monitors the voltage across that resistance. And due to that, the sensor itself is required to be thicker than the length of the prongs on a plug. So, it's not a great solution. But we have a great solution. Look at this. So here's a picture of our device. It's a sensor PCB that can be built directly into the faceplate itself. So there's a picture of the device installed. And in addition to having a lot slimmer form factor, it has integrated 802.15.4 wireless. The power consumption of the sensor itself can be a lot lower. Resolution is comparable, and the manufacturing cost of this device can be less than $5 in large quantities. So you're probably asking, how does this work? And the main technology that enabled, or the main idea that enabled such a slim form factor and lower power is the way we sense the current. So when the plug load current is changing, that creates a changing magnetic field. And if there's a changing magnetic field incident on a loop of wire, that generates a voltage. So therefore, if you have a coil, a number of loops in series, with a changing magnetic field incident upon it, you can measure that voltage to measure essentially the derivative of the current that is creating that magnetic field. So therefore, we can measure the current without breaking the circuit. And that's what enables the slim form factor. And since we're not adding in an additional resistance in the loop, it enables lower power dissipation in the sensor itself. So here are a few measurements from our prototype sensor. The top plot on the left is the voltage, nothing too interesting there. The middle plot is a measurement, that is the amplified output of our current sensor, so that's the derivative of the load current. And then the bottom plot is the middle curve integrated. So then that gives a signal which is representative of the load current. And on the right, this is a plot of the amplified output of our current sensor as the load current is varied. So you can see it's very linear, and our resolution is down to about 1 watt. So we think that that's sufficient for use, what we want this to be used for. So there are a lot of devices in this space. Kilowatt is just one of them. Where does this device fall in this space? And we think it's here. So we think we can sell this for a very low cost, let's say at Home Depot, a 3-pack for $30 with wireless connectivity built in. So low cost measurement with wireless communication is the application that we think this is best for. So in conclusions, I've shown you a panel metering solution that roughly could be installed for $250 per panel, and installation in 30 minutes, let's say. And also a wall outlet sub-metering solution. Just a rough estimate of $250 per residence. And you can do this very quickly, let's say 30 minutes throughout the whole house. So in conclusion, detailed building electrical energy data can be had for cheap and easy installation. So that's my contact information. Feel free to contact me if you have any questions. And I thank you for your attention.
This is a quick one. I missed it.
Sure.
It's $5 a panel, but $250 a house. How do you get up to $250?
So it's $10 per circuit breaker roughly. And then if there's 20 circuit breakers in a panel, and then you need some sort of base station, so it's roughly $250.
I'm sorry, I meant to say wall outlet.
Okay, so yeah, if we can build the sensor for $5 per outlet, sell it for $10 per outlet. Let's say you have 20 outlets in your house, and then you also need a gateway for $50. So that's how I calculated that.
So we heard this morning about the circuit breaker meters having problems with crosstalk. Do you have similar problems with your technology?
Yeah, we do, but we think we have some ideas about how to solve that. So stay tuned.
I'm going to have a quick question. So in the wall outlet, is the idea to have your circuit board, I guess, just be part of the wall plate? Is that the simplest way to do a replacement?
Here's the board, and this is just a 3D printed faceplate that, this fits in there, and then you can just take off the faceplate and screw this on, and that's all.
I'll buy one. Maybe more than one.
Hopefully this room isn't half of the room.
It looks like each individual sensor on each breaker needs to be individually calibrated. What's the process, and how long does that take?
Sure. So that could be a problem depending on the building, let's say. But if you say you can install, if all of the circuit breakers are similar and you can put each sensor in roughly the same place, maybe you can get away with not having to calibrate each circuit individually. But we also have some more ideas about how that we can actually do calibration automatically, and we think that is the next big step in something like this is the calibration, because it can be a pain if you have a building where you can't easily arbitrarily load each circuit. How do you do the calibration? And so stay tuned.
Great. I think that's it. I want to. Oh, is there another question?
So what the kilowatt has that doesn't have is the ability to walk over without any wireless, without any other computer, and just read what you're doing right there.
Yep.
Have you ever thought of something with a display on the other side for someone who doesn't want to turn on another appliance?
Yeah, it could definitely be done. Sure.
Great. Thank you.
Thanks.
I want to read